this GAT, which is the Graph Attention Neural Network. Okay, so the idea is we have one node, and at each time step, it gets updated with the surrounding nodes, and then there's this attention weight that will be updated by, okay, before going to a new node, okay, a new node hidden representation. So I was stuck here just now. So this is the function that was, this whole code was given by TensorFlow. Okay, I'm just trying to decipher what exactly is going on here because I'm new to graph networks and this is something interesting. Okay, so apparently over here, this is the init for the layer, the override the Keras layer. So this part is a standard one. Okay, the build basically is to build the trainable variables. Here, there's a kernel, which is given by 100 times, 100 is the number, the hidden units in the hidden layer H. Okay, and then over here, they use multi-headed attention. So there's 8 heads, so total 800. Okay, goes over to the hidden units 100. Okay, this kernel attention is 200. So I'm just trying to figure out why this is like that. So this part has been done just now. So the first part, it will require a nodes transform, which takes in the node states of this dimension, okay, and multiply by this kernel. Okay, so this kernel here, the input shape 0 minus 1. Okay, okay, so actually this kernel, when I checked just now, when I use the, so the kernel was actually 800 100. Okay, so it means that this part needs to change. Yeah, this is a really difficult code to understand actually. I would like to try to simplify it if possible. Okay, but I need to get good first. I need to understand more about graph neural networks before I can change it. So here the kernel is of dimension 800 by 100 actually. So this part here, the node states. Okay, I need to find out uh, what is the shape of this. So maybe I can just print out the shape here and yeah, maybe we could just print this out. Okay, and we do it here. So okay, in the training step, let's just do the training. Okay, we should print out the two states. Okay, so that was all I needed to do. So oh oh no, they lose the, there we go. So it is 2708 by 800 and 5429 by 2. 2708 by 800. Okay, so let's go back to that code earlier. So just write node states is 2708 by 800. Okay, and then ages is 5. Actually, this is the same as the initial one that we put in. This one, 5429 by 2. Okay, so now what we need to do is to find out what is this shape over here. So we could do this. Okay, we could do this just to find out what exactly is being done here in this first step. So let's just print out this one. I expect this thing to be node states transform. It should be, because the node states is this 2708 by 800. Okay, so this node states already has been pre-processed. Okay, because it's not 1433 anymore. So probably in the earlier layers there was a linear layer somewhere that does the pre-processing. Yeah, so it is likely that this is the code that does the pre-processing over here, and then later when we call the attention layer, which is our um, graph attention network, this is then passed into the code above. So this one should be 27. Actually, I don't think I need to print this out. I'm quite confident that this will be this already. Okay, because there's no need to print it out. I'm quite confident about this mat multiplication code. So this is the inputs here are basically the process inputs already. Okay, so you can see that when we do this, this is already the process inputs. Okay, that is why when we actually initialize this attention layer like that, yeah, the call is like this. When we initialize this, we actually, yeah, we actually don't have the information over here. The information that we have for the node states and edges are in the bottom level here in the model itself. Okay, when we go to the attention layer, okay, um, there's really nothing here. The main thing is just to first do a form of convolution. Okay, or not convolution, just a multiplication with a kernel. So this is like a matrix multiplication of, so the node states itself is our entire nodes hidden unit. So we can just call it like a vector h, and then we have this kernel here that does the transformation to it. So I guess we can just call it w. Yep. So from this node states expanded, node states transform, we do a tf dot gather, and this one we put in the ages. So when tf dot gather is used, okay, so let's say, let me just do a code here. When I do a tf dot gather, and then I have like maybe a matrix like 1, 2, 3, 4, 5, and then my next part here, maybe I have like 2, 3. Okay, maybe I do like 0. So if I have something like that, okay, it will return me like 2, 3. It will return me the indices for this. So if I like 2, 3, 5, it will return me the indices 2, 3, 5 over here. So this ages is actually of this size 5439 by 2. Okay, hence when we pass this in over here, this is something like this, like 2, 3, 3, 5, and so on. So when we do something like this, it basically takes the relevant indices here from this earlier part, and then it just puts them, concatenates them together. So it does this part here, it concatenates this together. Okay, so this whole thing was just to concatenate this. So we can treat this as node states expanded concatenates the hidden representation of both nodes present in the H pair. Okay, then when we do this, we reshape it with this tf dot shape ages 0, which is this one. Yep, and then -1. So we basically reshape it to make it two dimensional. So maybe what we can do is we can just print, okay, to just find out why we need to do this reshape. Maybe I just print out the states here. So I just print this out, and then we just see what it looks like. Okay, so initially without doing the reshape, okay, it seems that it is a 5429 by 2 by 100. Okay, the reshape makes this 200. Okay, so let's go back. So node states expanded shape is, okay, this one will be 5429. Is it 39 or 29? 543, 5429 actually. So this is 5429 by 2 by 100. Okay, because it is having two indices over here by 100 different like hidden representations. So this is 3 2. Actually, it should be 102. So it depends on the ages dimension. Ages dimension is 54292. So we pass this down over here. Okay, when we do together, it should give us 200 over here. Okay, where was I? Okay, maybe I hide this part here because it's sort of making it a bit long. Okay, let's see. How do I hide this cell? Okay, I thought I could hide the cell by clicking on the outside here. Okay, maybe we just remove that. Okay, so if we were to do this over here like that, this shape here is 3 comma 2. So yeah, the output tensor will give the same shape. So I guess a TF dot getter of this one by this one. Okay, since the node state transform here is 2708 100, so when we do this we will get 5429, which is the ages here, by this one two sorry by yeah, by 2, because you choose 2 elements, but each element contains 100 hidden states. So it is something like this. If let's say over here contains, like over here, let's put like 4 hidden states here. Yeah, let's just for simplicity put the same number. So if let's say each of them have 4 hidden states, okay, and then we do a gather. The end output should give us, okay, because there's a total of 3 prompts here. Okay, each of the prompts have 2 different indices, and each of the indices contains 4 hidden states. So it should be like that: number of prompts, number of elements in the prompts, and then the number of elements or the vector size of the hidden state. So when we do like tf.gather, yeah, it should give us this 5429 200, and then we make it a 2D shape. Make it 5429 200. Okay, so this is the attention part. So they were calculating this bit. You take the hidden representation and you concatenate them. Okay, so that was this bit here. Okay, so yeah, this is the reshape part. Okay, we are done with this. I can delete away this. Okay, so next part here is the attention. So the attention score, they use a Licky ReLU, and then they did a map multiplication with this node states expanded and kernel self attention. Okay, so it appears that the attention weight is not using like a key value pair kind of dot product, uh, or query key dot product. Rather, there's no dot product at all. It is just self-learned through a kernel attention matrix, like over here. And then when we do this map multiplication here, so okay, let's just do it out in full. So the node state expanded shape is 5429 200. Okay, then the kernel attention shape is, okay, so this is actually already 200. The kernel attention shape is 200 by 1. Oh, I see why they do 2 times this one already. I understand this code now. Okay, it's because of when you concatenate this part, you you concatenate the hidden representation of 100, it becomes a 200. And so when we like do a sort of like attention, we want to like make it back to 54291. Yep. And then when we do this squeeze over here, so this squeeze, okay, should give us 5429 comma, okay, because when we squeeze this, when we do a squeeze over here for TensorFlow, it removes the dimension of size 1, okay, and the axis they put -1, which is the last axis. So if we squeeze this, like over here, 2 3, okay, that's weird. I mean, this was so all the size 1 will be removed, size 1 1 1 1. So in this case, this size 1 should be removed. Okay, so I mean, we just print the shape here just to check it out, and the shape here just to check it out. But I'm quite sure that this is what is happening, okay, at the back end. Yeah, correct. So this is what is happening for the attention weights. Okay, so it appears that it's not really like transformers. You don't really have a key value product here, or a query key multiplication like here. Like this is what you do in the transformer. You don't really do this query key thing. What is happening here is just you multiply by an attention matrix, which is learnable through backpropagation. And same thing when we do like transformation of our states, we also learn like this kernel here, which does the linearly transform the node states to a hidden representation of size 100. Yeah, so yeah, so the output here is num times 100. Yeah. So this is the linear transform. Okay, I understand this now. Okay, then we get the concatenation here. Okay, we shape this concatenation. Okay, and then we put them together over here with an final attention weight. Okay, and this attention weight is based on this kernel attention, which is learnable by backpropagation. So yeah, looks okay, looks okay. I understand it now. So this 5429 is the connections of the ages in the graph, and in this case this is the Cora data set. These are like which papers cite which papers. Yeah, so over here this is um yeah, okay. So what we do is given okay, I guess we need to do a mat multiplication here, because like for each of the nodes here you use the, or rather for each of this 5429, I guess, ages of concatenated nodes, yeah, we need to sort of like multiply it by a certain score in order to get like 5429, which means that this 200 is the hidden representation of each of these pairs. So we basically convert this hidden representation into a single scalar value. Okay, and then this scalar value, what we need to do is then okay, what they did was to normalize it, to clip it firstly between -2 and 2. This is quite important for neural networks, because if you don't clip, you might end up with very high numbers, which may make the training not very stable. So they did a clip here, and then they did an exponential, okay, before taking a math.unsorted segment sum. Let's take a look what does that do. Computes the sum among segments of a tensor. Okay, so let's see. So this is my data, and this is my segment ID. So I specify which of the elements to add, and then I add it in. And then why is this 9? Okay, this 13, 7, 2 plus 4. And this is, oh, this is why it's not segmented. So it's 5, 1, 3, 6 plus 3, 9. So I guess this is your data. This is your segment IDs, and this is your number of segments. So what is my segment IDs though? num segments. Okay, let's see how it does. Okay, this is the array, and then we have a segment 0, 1, 0 means basically the middle element, and then num segment is 2, so we get this. What if we put num segment is 3 though? Yeah, so let's copy and paste this code to try it out ourselves here. Okay, let's try it out. Let's try it out what this does. There's a lot of very TensorFlow specific stuff here that needs to be sorted out to understand this code. Okay, so if there's 3, okay, it means that it will split into the segments, but what are those extra segments here? Okay, what if I specify more things here? What if I specify this as 1, 0, 0 like that? What will happen? What will happen here? Oh, 3, 4 does not start with. Okay, so I guess if I do this, I need to have like 3 segments maybe instead of 5 segments. Okay, I got this wrong. So a segment ID, a tensor of shape is a prefix of data dot shape. Okay, segment IDs need not be sorted and need not cover the full range of values. Okay, so maybe I need to have like 2 segments. Okay, so I'm a bit confused here. Um, okay, so I want to make this segment sum contain both segments. Am I doing it wrongly? Data shape is 3, 4. Okay, so I guess I need to specify like I need to have starting segments of 3. I cannot have this like that. So I guess what should happen is that, okay, let's just try one more. So I kind of need to like specify my original. I'm not sure. Okay, so this sort of gave us this instead 23, 23, 0, which is maybe like this 0, 1, 0, 0 is you take 0 for this one. We basically sum up this one 2 plus 6 plus 3. Nope, it doesn't work that way. Yeah, I'm confused what this segment IDs do. No idea what this does. Okay, let's see the code below to just see what's happening over here. So we have, okay, I know this is to clip by value, so this does the softmax, but clips the exponent between -2 and 2 to prevent gradient overflow or underflow. Okay, what does this thing do then? What's this math unsorted sum? Okay, so we have the attention scores, which is of this shape 5429. Okay, and then we have the ages. The segment IDs is the ages 0, which means the first node, the target node. So the segment IDs is the first node itself. Okay, so they are basically checking the neighbors of sum up the attention of the original of only the. So I guess the segment IDs, we just basically pick only the first one. Okay, and what we'll do is we'll then TF reduce max ages, this one plus, okay, let's just, I'm I think TF dot reduce max just counts the maximum of the elements in that value. So it's like reduce max here, this is, oh, this is a count. Okay, this counts, no, it calculates the maximum elements across dimensions. So if like you do this, you are supposed to get -1 because it's a maximum. Here is a nan. Okay, so it just returns the maximum. It's just a fancy way of saying maximum using TensorFlow. Reduce max is actually the same as using the max operator. So we do a max over the target nodes plus 1. So yeah, I'm quite curious what this ages is, because this ages is like that, and based on what we see in the ages matrix earlier, the ages matrix is like this. So if we do a maximum of the ages matrix, what does that mean? This is so difficult. I mean, just understanding the first line took about 20 minutes already. This is made tougher because I don't quite understand all this TensorFlow stuff. Okay, but I think what they are trying to do here is, maybe I should print out ages and take a look at what ages is, so that I can, like, sort of understand it better. Okay, so we see ages is a tensor like this. Shape is 54292. So it's like this, 404000. Okay, so we kind of need to find out what's inside these ages. So let's see whether we can do it. We do exactly what the code asks us to do. We'll see what. Okay, so it's a strided slice. Shape is 5429. Okay, what are the values for this? Hmm. There we go. Okay, let's just print the tf.reduce max just to see what this is. Okay, so it's not printing out here because this is not compiled yet. I guess if they use like tf.function, this is a static graph. So we need to use tf.print so that we can print out the value of whatever is there in the static graph. Let's go to tf.print instead. Okay, rather than print, because print will only run one time when we first run the loop, but tf.print will be part of the graph itself. They will print out the value of this, whatever we are doing here. So let's wait a while. Okay, it's not printing out now. There we go, 1897. Okay, so apparently this, I think, counts the number of nodes that are referenced inside there. Where was I? Yeah, maybe we can now do the printing out of this entire thing. Ages, I think in this case ages will just be probably just a one hot encoding. One is when it's present, zero when it's not. Okay, let's just see what this is. Yeah, this code is sure hard to understand just by looking at this. Okay, so we can see this is already what's happening. So it looks to me like this is still the node numbers. So why are they taking maximum though? Because this feels to me like it's still part of this. If you look at the ages graph, okay, the ages graph is like that. The paper number, the target paper number, and the source paper number. So you can see like it's up to 1897 2707. So it's up to the source paper of 1897 linking to the next source 2707. So I'm just curious why they did this, because like when we sum up the okay, this attention part I understand already. Okay, this one I understand already. Attention scores, they did an unsorted segment sum over this attention scores, and then they sum up over um, whatever segment IDs that are in the target. Okay, and then the num segments will be the number of targets, I guess, plus one. Okay, so attention score is this shape. So they did like matching one. I guess if you want to do here, the shape is four over here. Sorry, the shape is four inside here. So we kind of need to put four inside here. Okay, let's see if we were to. So this ages zero is like um a total of 5429 ages as segment IDs. So the num segments here should be, I don't know, this 54290. This is 5429. Mm, no idea what this does. Okay, this is a very weird way of coding it. It's very weird. I mean, then after that, this is basically just repeating the attention score sum across this number of binary counts. Basically, it just counts the number of ages, I guess. Yeah, it repeats that number of times, and then you divide the attention scores. I mean, you could just put this as 5429, but I guess this is a fancy way of counting the number of ages in the graph. Yeah, this bin count is just to count the occurrences of each value. Oh, it counts the number of occurrences. Okay, different. So it's like over here you have 1, 1, 2, 3, 2, 4. Then the number of zeros is zero, number of ones is two, number of twos is two, number of threes is one, number of fours is two. Yeah, okay, so this counts the number of occurrences of each paper. I understand this now. Okay, of each paper. Okay, you count and then you put inside an array. Okay, and then we just divide this. So basically the attention score will be divided by the number of papers. Okay, attention scores divided by the number of uh, nodes linked to target node. Okay, so this attention scores repeated by okay, tf dot repeats. Okay, so this is the initial one, and then you have the number of repeats at the bottom. So tf dot repeat is my initial sum for the attention scores, and then repeated by the number of nodes that are linked. And then what we do is we take the total attention score and divide it by this. Yeah, I mean, I guess this part just does like you need to repeat this attention scores sum Okay, because this is like a certain fragment of it, then you need to like repeat it for the number of times it occurs, I guess. Then you then take this and divide by here. I mean, this is quite fanciful way of doing it. I'm sure there's an easier way of doing it. This is not very easy to understand. This code, yeah. I mean, first I don't quite understand this part here. Okay, this is unfortunately hard to read. Okay, yeah. Well, I mean, yes, Google researchers are pretty proficient at their own system, so this is something normal to them. But for someone trying to understand this code, it's quite a headache to understand it. At least I understand like more than one part. Okay, like two parts already, so that's good. Um, I probably need to print some stuff out to understand what is going on. So these attention scores, I know it is. So let's just print out the attention scores sum over here, and then we also print out over here. Then we print out the attention scores norm also. Okay, so that I probably can understand what is going on. Okay, let's try to understand what's going on. I'm not even done like trying to configure yet. This is just trying to understand what's going on, and it's taking so long already. Okay, so yeah, way to go, neural networks. Yeah. Okay, so unsorted segment sum, it's shaped. Oh, okay. So they still cannot do this because this is not runtime yet. So this I cannot understand the shape from here. Okay, but we get the final shape to be 5429 at the back. So this final shape here is in the end is still back to 5429, where I guess basically each node will be normalized by the number of neighbors it has. So yeah, it will be normalized by this. So I'm just thinking why they put attention scores here. So attention scores is this original one, and then what we do is we normalize them by the sum. But when we do this thing here, when we do the tf dot repeats, it doesn't take into account the order of where it appears. You see, it just repeats directly like BBB, like 1 2 3 4, repeats 2 3. This is like repeat the first one twice, repeat the second one 3 times. So if we were to do something like this for the attention source score sum, we would not be preserving the order of this thing here, isn't it? Ah, I get it already. Okay, because when we do the segment IDs here, okay, we group by ages. Okay, so this one is like uh we already sort like the first segment is only for target node 0, second segment is target node 1, third section is target node 2. No, sorry, yeah, correct, third segment is target node 2 and so on. So this already sorted by target nodes. So when we do this here to repeat this, it will exactly fit into whatever we have summed up here. So if let's say your node appears 2 times, then this will have 2 times also. Then when we take the attention scores, okay, this part here divided by this part here, you are basically taking each of the target nodes. Okay, in this attention scores, okay, is divided by the number of nodes linked to this target node. The shape is still preserved. Okay, so this very complicated operation is basically uh, rather than doing a for loop inside this, which can be very costly, this is using a matrix operation. Okay, over here is using this math unsorted segment sum in order to sum up all the attention scores belonging to the same target node. Okay, so I'll try to implement this up here. So so let's say this is Okay, let's try to keep it similar to this context here. Our attention scores data is 5429, so let's just make it an array of like a few numbers. And then what we do here is maybe we just take the target. In this case, the target will be like somewhat like 1 4 5. Let's say we only have this target, and then we put num segments as 3. Let's see what we get. Okay, so maybe we need to have something like 1 4 5 like that. Okay, so my initial one is 5429. Okay, and then we have this attention scores here, which should also be of this same shape. Okay, what shape is my segment IDs here? Ages 0 is, I believe, of shape 5429 also. But we have different segment IDs here. Okay, so maybe we just put this whole thing here. And then the num segments maybe is 9. Actually, it should be 10. Okay, so the num segments down here will be the maximum number of target nodes, I guess, plus 1. This is very weird. It's very weird. I mean, what if I have more number of segments, right? Okay, so I guess more segments should be fine. It still work. Okay, we only have one. You see, you just make it 0 here if we give more segments. So over here, the number of segments will really just be based on the number of target nodes. It's more or less, it doesn't really matter, okay, because it will be counted here later. So the idea here is just to get, I don't know, so let's say we have like some targets here, and then the num segments maybe to 6. Okay, we need to have the same value, so let's just put some numbers in. 1 2 3 4 5 6 7 8 9 10. Okay, so we have a different number here, so 9 8 8 6 0 14. So 0. Okay, let's just put more segments. Okay, I'm not too sure how we got all this, so like this is 4 2 5 5 5, so it's 0 5 5 5 5 3 2 1. So I guess segment 0 consists of 9. Segment 1, oh, so this is the segment numbers. I see. Okay, I understand it now. Yeah, so this is segment number 1. So segment whatever you, oh, all right, right. Okay, so this is to say that whatever data over here, you give it the segment ID, either segment 0 or segment 1 or segment 2, and then it will sum up accordingly based on the segments. So this will just give me the index for what segment. So segment 1 is 8. Okay, segment 2 is 7. Okay, but because I also put here, so 7 plus 1, so it's also 8. Segment 3 is here, which is 6. Segment 5 is this one, this one, this one, this one. Oh, sorry, segment 4 first. Segment 4 is 0. Segment 5 is 2 plus this 4 over here, which corresponds to this 4 here. 2 plus 3 plus 4 plus 5, which is 5 plus 4, 9 plus 5, 14. And then segment 6, 7, 8, 9 are all 0 because they don't appear at all. Okay, but the number of segments will be actually equals to the size of this thing here plus 1, or actually rather it will be the maximum element inside here because that's the maximum segment number. Okay, over here this is the maximum segment number. So the maximum segment number will definitely be the maximum. So maybe I just explain over here. So the segments are labeled by target nodes, and each segment will be the total sum of all the different components with the same label. And then the number of segments is just the total number of target nodes, which is here. And they did a plus 1 also because there's also the null set where we don't have anything. I mean, we can also do without this plus 1, I think. Yeah. So this will just repeat, and then they will divide by attention score if no. Okay, so the last part here. Okay, so I think we got this part here already. We got this part done. So we have the softmax thing, and then we sum the incoming edges node to add up to 1. So we actually need to do this normalize thing, which I think is already done. Like we normalize it here, and then after that what we do is, okay, because we divided by the total sum of nodes to that particular node. So when we do this thing here, this will already give us the normalized attention weights across only one node. Okay, so this very weird and hard to see because it's all matrix multiplications just for this GNN. I mean, if you do it with a for loop and then you like add up the messages together in that for loop, it will be very easily readable, but at the same time, it loses out on the fast hardware accelerations you can get using a GPU. So this code is actually quite efficient, okay, because it does everything like a matrix multiplication, which will work very well on the GPU. So now the last part is to gather the node states of the neighbors, apply attention scores, and aggregate. So we basically find out what are the source, or basically the destination of each of these nodes. We gather this for the neighbors. Okay, and then same thing, we do the unsorted segment sum with for each neighbors. Okay, we multiply by the attention score norm. Okay, which is this thing here, this normalized attention score. Yeah, so maybe I should put here like for a given target node, for the neighbors of a given target node, the attention scores sum up to 1. Okay, so we have this. Okay, we do this unsorted segment sum. We take the data as the neighbors original hidden state, okay, weighted by the attention score norm. Okay, so yeah, this is our data here. Just thinking whether it can multiply or not, because the attention score norm is of the shape is 5429. Okay, I'm just thinking whether or not when we do 5429 here, what is this thing? Is node states neighbors. Okay, if we go by what we saw earlier, it will be like this 5429 200, but in this case because the ages are just only 1, so this will be 5429 by 100. So if we take 5429 by 5429 by 100, we should be able to like weigh each of this neighbor's hidden state, all these elements. Okay, by the attention score itself. There can be broadcasting. Okay, but over here, they did do a new axis here, which means that yeah, this is to help with the broadcasting. Yeah, means we multiply 5429 by 100 with 5429 by 1. Yeah, so after that we take the segment IDs, which is the, in this case, it's the still the target node itself. Segment ID is still the target node. This is the neighbor node, and then the num segment is the number of nodes. Yeah. So this whole code just aggregates up the attention scores of the neighbors like this. We apply the attention scores to the hidden state vector, and then we add it to the new node state for all of the nodes. So this is how it looks like. Where was it? Yeah, here. And then we return this aggregation. Okay, that was a difficult thing to understand. Okay, I think I get it now. Okay, so now what I'm interested to do is to see, like, okay, right now, oh, okay, let's stop printing out some stuff first. Okay, so now that I got the gist of it, I'm gonna try to tinker around the code another time. Okay, just to, make sure that I understand what's going on. But I'm just thinking, because the number of connections is so little, okay, can we actually get the same performance uh without any linkages at all? So let's try it out. Okay, let's just try out the normal method first, and we see whether it works. So restart and run now, maybe. Yeah, let's restart this whole thing and run now. We see how it works by default first, and then after that we see whether I can just like tinker around and see whether it works again. I'm thinking that actually, because this is not really there's not many connections. If you look at the connections we see earlier, the number of papers that cite each other, there's like a lot of them that have zero sightings of each other. So it's like almost half the data set have zero citations. So I'm just curious, with such a sparse graph like that, will graph neural networks actually be useful? Or is the output solely based on the hidden features itself? Because it could be just with the hidden features, you can already get the output. So that's something. But I remember this one, if you just use these hidden features without the graph, it doesn't do that well. So there might be some linkages to the graph, because papers that are similar, they tend to cite each other. So there could be some use for that. So it's about 78.5%. Okay, now what I want to do is I want to basically take away the ages. Okay, so what we do is we have this thing called new ages equals to ages 0. So maybe we just pass it the new ages. So this was 80% accuracy. If we just remove all the age information, okay, what's happening? Okay, let's see what the shape of new ages is. Okay, 021. Okay, 54292. How about new ages? It's just like 2. Yeah, so we need to make it of a shape 1 2, basically. So got, Yeah, so you only have one link. Okay, in this case, I bastardized the graph. Instead of having the citations in the Cora data set cite each other, I just basically have only one link, which is the first paper, like 0 to 21. Yeah, so we see what's the accuracy like, and it's about 73.9. I wonder if I can just do away with everything. Like, I'm not sure whether I can do like a 0 to here to show that there's no link. Yeah, I think I still have to give at least one age. If not, I think it'll be difficult for the program to run. Okay, let's just try maybe age 5. I don't know. So it does seem that the ages help, but it doesn't really help that much because I take away all the ages, it still does the update pretty well. I mean, the graph attention part works only when there's ages. If let's say a node is not connected to anything, it is basically just using the node's information by itself. It's not too bad. It's like 33%. You see the accuracy of the predictions down here. Still not too bad. Okay, so the Quora dataset can be said to be quite an easy one, I would say. It's doing still quite well. Yeah, I think it's maybe, you know, I don't know, maybe increasing the hidden units might be better because like we might have over compressed our information with only 100 hidden units. Maybe we need 200 hidden units to make it work better. So I just put 200 here. Okay, the rest I don't change. I guess this one can play around with it another time. Yeah. So I think this should be better. And take oh no, we only have one link here. Okay, we only have one link because I remove all the links. Okay, so it's about 74%. So if let's say I were to use this as ages, which means that I don't remove the links, I use the full links. Okay, that was 34% if I remove all the links. Now I put back all the links in the data set. Okay, what will my accuracy be? So it looks like the links do play a role in this graph neural network. Okay, the accuracy is higher. Okay, with this. So I'm just wondering, okay, let's go back to 100. If I increase the time steps to like 10, okay, which means that I link more and more and more. So you can go up to 10 hops. Okay, if I link one means only one hop, three means three hop, 10 means it can link to 10 neighbors. Will the accuracy be better if I can link to 10 neighbors as compared to just linking to three neighbors, which is what is happening in this code? So I'll just do this last experiment, you would say, and then yeah, I think I'll call it a day. It's quite late here. So let's take a look whether this is possible. Yeah, this is a quite interesting code actually. Whoever wrote this is really quite good with TensorFlow. Okay, I really had a hard time understanding it, but I think this is a very efficient implementation of the graph attention network. If I were to implement it, it will probably be in a for loop, which will be very inefficient. So okay, we can see some issues already. The loss is nan, okay, which means that there's an issue with gradient explosion if we do this. So perhaps some form of layer normalization will be required if you increase the number of layers. Okay, if not, your gradients might explode too much. Okay, and with that, I shall end here and probably continue tinkering around with this neural network in a future session. Yeah, thanks for watching and see ya.